In the stillness of an endless night, the cosmos drifts in quiet harmony. The vastness of space stretches out, silent and serene, a canvas of darkness spangled with gentle starlight. Here, far from any earthly sound, there is a hush older than time, an ancient silence that envelops everything like a soft, cosmic blanket. It is in this profound quiet that the universe seems to hum a lullaby, a subtle song carried not in sound, but in light and gravity. Each distant star flickers with a faint and tender glow, each galaxy a distant chord in a melody only the universe can hear. The silence of space is not the silence of nothingness. Hidden in the quiet is the faint whisper of creation itself. A soft afterglow of the beginning still lingers, filling the darkness with an almost imperceptible warmth. Though our ears cannot hear it, the night sky above is alive with this ancient echo. It is a gentle background glow that bathes the cosmos, a remnant of the universe's first light, stretched thin and cool over billions of years. This is the cradle song of the cosmos, the cosmic microwave background, a faint memory of the fiery birth of all things, now calmed into a soothing murmur that pervades space. Under this quiet glow, the universe has been sleeping and waking in rhythms far longer than any human lifetime. Stars are born and die in distant corners, yet from here it all feels still, almost motionless. Drifting between the stars, one can imagine the universe breathing softly in its sleep. In the darkness, a traveller would find no up or down, no day or night, only an eternal expanse where time itself flows like a gentle river. It is a realm of vast distances and deep mysteries, but it welcomes us with peace and wonder. In this tranquil abyss, even the grandest of cosmic events unfold in majestic slow motion. The collisions of galaxies, the births of stars, the dance of planets, all transpire in such grand scales of space and time that from our perspective they seem almost frozen, like a tableau of silent beauty. Yet nothing is truly static. The stars overhead may appear fixed in their constellations each night, but they are journeying on their own immense paths. Galaxies rotate languidly, their spiral arms moving as if in a slow waltz, entirely imperceptible to a single night's eye. And threading through this calm, dark expanse is an invisible tapestry, a delicate lattice of gravity stretching across the universe, quietly guiding the dance of galaxies and stars. Though unseen and silent, it holds the cosmos together, whispering the instructions of creation. Floating in this darkness, it is easy to feel a sense of eternal calm. Imagine gliding through the void between galaxies, surrounded by millions of light years of solitude. The only light comes from far-off stars, their glow soft and ethereal, like distant lanterns in a sea of night. There is no rush here, no noise, only the slow, steady pulse of time and the faint radiance of starlight to keep you company. In such serenity, one can sense how the universe holds its secrets patiently, cradling them as a mother might rock a child to sleep with a lullaby. The universe has stories to tell, but it whispers them. It invites us to listen closely to the silence, where every faint glimmer and shadow has meaning. In this gentle hush, we begin our journey through darkness and wonder. We drift back to the very dawn of time, to witness how this peaceful cosmos emerged from chaos. The silence we feel now was not always so. It had a beginning, There was a time when the lullaby was a thunderous song, when darkness blazed with unimaginable light. But as with all songs, the universe's melody began softly after its first explosive notes. So now, in the spirit of a calm night under the stars, we journey back to hear the echoes of creation, reverberations of the universe's birth that still resonate as a quiet hum in the darkness today. Long ago, before the first stars broke the darkness, all of space was filled with a primal light. In the beginning, the universe was born in a moment of unimaginable brilliance and energy. What we call the Big Bang was not a conventional explosion, but an expansion, an instant when time and space themselves unfurled from a single primordial point. In a fraction of a second, the cosmos grew from smaller than a grain of sand to vast beyond comprehension. This newborn universe was searingly hot and radiant, a glowing fog of particles and light tangled together. There were no galaxies then, no stars or planets, only a bright, dense sea of energy and elementary particles, all intertwined in a youthful chaos. As the universe expanded, it cooled, ever so gradually calming that ferocious brilliance. Within the first few heartbeats of cosmic time, particles joined to form the nuclei of simple atoms like hydrogen and helium. The cosmos was still a blinding haze, with light scattering in every direction, unable to travel far without meeting a particle to bounce off. It was as if the universe was lit from within by a brilliant fire, but that light could not yet escape. It was trapped in an endless game of billiards, ricocheting between particles in the opaque plasma of the early universe. In that hot, dense fog, pressure waves rippled through the plasma, deep, resonant vibrations rolling across the young cosmos like the muffled notes of a cosmic drum. Eventually, after about 380,000 years, a brief infancy on cosmic scales, the universe had expanded and cooled enough for electrons to settle down with nuclei, forming the first atoms of hydrogen and helium. And with that simple act of union, something profound happened. Space itself became transparent. The blinding fog thinned and vanished. Light that had been locked away suddenly was free to stream across the cosmos. The universe, for the first time, grew dark to the eye, but not before releasing a vast sigh of light, an afterglow of the Big Bang rushing outward. That first light is the echo of creation, still humming all around us. Those photons that streamed free when the universe took its first breath have travelled for billions upon billions of years. They have stretched and cooled with the expansion of space, their once fierce glow now gentle and cool, transformed into microwaves. Though invisible to our eyes, this light bathes the entire cosmos even now. We caught its whisper with instruments in the late 20th century, confirming that the sky itself holds a memory of when the universe was young. This faint afterglow, this cosmic microwave background, is a portrait of the infant universe, a nearly uniform glow with tiny ripples that were the seeds of everything to come. After this release of light, a great darkness fell. With the brilliant primordial glow now faded into the background, the cosmos entered a deep night that would last hundreds of millions of years. There were no stars shining yet, no new light, only the soft afterglow dimly illuminating the darkness. The universe was vast and mainly featureless to the eye, filled with transparent hydrogen gas and the unseen presence of dark matter. This was the cosmic dark ages, a period of quiet and shadow. Yet in this darkness, the stage was being set for the first dawn. In the silent dark, gravity began its patient work. The newborn atoms, mostly hydrogen, drifted through expanding space. Here and there, ever so slightly denser patches of gas and invisible matter drew in more and more of their neighbours. The primordial fireball's faint irregularities meant some regions held a touch more matter than others. Over time, those regions became gathering points. Slowly, imperceptibly, the darkness was pooling into invisible clouds and filaments. Though nothing shone yet, the universe was beginning to take shape in the shadows. These were the first threads of structure, assembling quietly under the guidance of gravity. In time, they would weave the cosmic web that underlies the galaxies. But for now, all was still dark and expectant. Drifting through this abyss would have felt eerily tranquil. No light to guide the way, only the distant, pervasive murmur of that creation echo surrounding you. But the peace of this dark cosmos was the peace of a universe waiting to be born anew. The echoes of the Big Bang still reverberated in the background, while ahead lay the promise of the first stars. In the emptiness, the atoms that would one day ignite were gathering in secret. The universe held its breath, poised on the brink of a great transformation. The quiet afterglow of creation was about to give way to the first true lights in the darkness. In the darkness, an invisible hand was at work. While the young universe lay in its long night, a mysterious form of matter was gently sculpting the future. This substance was dark matter, an enigmatic presence that neither shines nor reacts to light, yet outweighs all the stars and galaxies we will ever see. In fact, most of the universe's matter was this dark kind, far more abundant than the ordinary atoms that make up worlds and living beings. Even now, its true nature remains unknown. We know it only by the gravity it exerts. In those early ages, dark matter moved freely through the cosmos, gathering into clumps and filaments under its own gravity. It was as if the universe were tracing a delicate design in secret, using threads of this unseen material. Though no eyes could witness it, vast structures were beginning to form, a scaffold of gravity that would become the backbone of the cosmos. Tiny fluctuations left from the universe's fiery birth guided this process. Where there was just a touch more matter than average, gravity drew even more in, and those regions grew denser. Dark matter, unbothered by the cooling light and thin gas around it, pooled into diffuse halos and elongated strands. Over millions of years, these strands stretched out like the filaments of a spider's web, and the halos became the nodes where the strands intersected. Along these invisible avenues, the ordinary gas, the hydrogen and helium atoms born from the Big Bang, began to flow, pulled inexorably by the gravity of the dark matter. They gathered like morning dew on a web, collecting in greater quantities wherever the dark matter concentrations were highest. Slowly, quietly, the cosmic web was woven. If we could speed up time and watch from afar, we would see a faint network blooming in the darkness. It would appear as a ghostly lattice spanning the black, with threads intersecting at knots. These knots were the cradles of future galaxies, concentrations of matter where gravity was strongest. Inside them, gas was condensing, heating up as it fell into deeper and deeper gravitational wells. The universe was preparing its first nurseries for starlight. Through countless ages of darkness, this assembly continued. Smaller clumps of matter merged into larger ones, as streams of gas and dark matter flowed together. The structure of everything was set in place before any star ever shone. An intricate map drawn by gravity's hand. Even now, billions of years later, galaxies cluster along those same ancient filaments, like flowers blooming on invisible vines. But back then, during that epoch of night, the web itself remained dark. It was a silent framework, waiting for illumination. Amid this vast construction, the temperature of the gas in the densest halos began to rise from the pressure of collapse. In these pockets, conditions were quietly reaching a critical point. What had begun as diffuse wisps of hydrogen were turning into tight knots. Gravity kept pulling tighter and tighter, compressing gas in the heart of those primordial clouds. Unseen and unheard, deep within cold, dark halos, the first sparks of change were imminent. The cosmic web had gathered the ingredients, and now nature was ready to strike a match. The long night of the cosmos was ending. In the blackness, within one of those dense, unseen clouds, the very first star was about to be born. It would be a moment as transformative as the first cry of a newborn, the darkness making way for light. All across the cosmic web, other dense clouds were on the verge of the same collapse. The tapestry of invisible matter and gas had done its quiet work, and the stage was set. Soon, pinpricks of starlight would shimmer into existence as the universe's earliest stars ignited. The patient weaving of the cosmic web was about to reveal its purpose, to light up the cosmos with the first dawn. One quiet, dark corner of a primordial cloud suddenly gave rise to something entirely new, a point of light. At first, it was a faint gleam, a warming of the cold gas as atoms crashed together harder and faster. Then, in a surge of energy, true starlight ignited. Deep within a collapsing cloud of hydrogen, the temperature and pressure soared until hydrogen atoms fused into helium, releasing an immense outpouring of light and heat. The first star had been born. In that instant, the universe was no longer lightless. A brilliant blue-white star shone against the black backdrop, its rays streaming out to illuminate space that had never known direct light. It was the dawn of the cosmic morning. That first star was unlike any that twinkle in our skies today. It was likely colossal, hundreds of times more massive than our sun, and millions of times brighter. Fueled by pure primordial hydrogen and helium, it burned its nuclear fuel ferociously. Where once there was only darkness, now there was a beacon, pouring ultraviolet light into the surrounding void. And this lone star was just the beginning. Soon, in other pockets of the cosmic web, more stars kindled. One by one, across millions of light years, tiny glimmers appeared as other dense clouds collapsed under gravity's embrace. These first stars were solitary and far apart, each separated by great gulfs of darkness from any other, like lone campfires kindled on a moonless night. The cosmos, which had slumbered in darkness for so long, was waking up to a sprinkling of starlight. This period is often called the cosmic dawn, the end of the universe's dark ages. Like the first faint colours in the sky before sunrise, the light of early stars was sparse and isolated at first. But as these pioneers multiplied, their collective glow slowly pushed back the darkness. The energetic light from the newborn stars began to cleanse the universe of its remaining fog. Their ultraviolet photons struck the surrounding neutral hydrogen gas and split atoms apart, turning them once again into charged ions. Gradually, bubble by bubble, the murky veil of hydrogen that filled space was evaporating. What had been an invisible, obscuring mist was now clearing under the assault of stellar light. Over hundreds of millions of years, the universe transitioned from an opaque dusk to a transparent dawn. The first stars were reionizing the cosmos, allowing light to travel freely once more. High above the silent infant galaxies, if one could watch, the scene would have been breathtaking. Pinpricks of light twinkled in the dark like the first stars of evening, each one a massive sun blazing in youth. Around them, faint halos of ionized gas grew, like incandescent bubbles inflating and merging with their neighbors' bubbles. A delicate glow began to permeate what once was total blackness. The heavens were no longer void. They were dotted with the fires of creation. Where darkness had ruled, now there were stars, beacons of hope and heralds of change. Yet these first stars lived fast and died young. In a few million years, blinkingly brief on cosmic timescales, their fuel would run low. For a star so massive, the end comes in a dramatic crescendo. As the core can no longer sustain its fusion, it collapses swiftly under its own gravity, igniting a final cataclysm. The star detonates as a supernova, a titanic explosion unleashing more light in a single burst than 1 million normal stars shine in their lifetimes. For a short time, the dying star outshines entire galaxies. Its brilliance floods the surrounding space, a cosmic flower blossoming in sudden, tragic beauty. In that supernova flash, the star's contents are cast forth into space. Heavier elements forged in the star's heart, carbon, oxygen, nitrogen, and more, are scattered like seeds on the cosmic winds. These elements are the gifts of the first stars to the universe, the stuff from which future worlds will be built. In the ashes of those explosions lies the calcium that will one day form bones, the iron that will course through blood, the oxygen that will fill lungs. The universe was no longer composed of just hydrogen and helium. It had been enriched with the ingredients for planets and life, spread far and wide by stellar altruism. Some of those early giant stars met a different fate. Instead of exploding, the most massive might have collapsed entirely inward at the end of their lives, imploding to form something new and strange, a black hole. In those cases, the star's light didn't get one last blaze of glory. It simply vanished, leaving a dark remnant in its place. Whether through spectacular supernovae or silent collapses, the first generation of stars transformed the cosmos. They filled it with light and enrichments, and in dying, they sowed the seeds of new cosmic phenomena. As the debris of ancient supernovae mingled with primordial gas, new stars began to take shape in those enriched clouds. Each successive generation of stars was a bit different. Containing heavier elements, they could burn longer and steadier. Over time, this would lead to stars more like our own sun, long-lived and surrounded by planets. But in those early epochs, the cycle of star birth and death was only just beginning. Amidst the newborn light of the stars, another shadowy marvel was taking form. In the hearts of the heaviest collapsed stars, invisible gravities began to lurk. The age of starlight had given birth to darkness incarnate. The first black holes were about to emerge from the cosmic womb. A new kind of darkness had entered the cosmic stage. Where a massive star's life had ended, a shadow of unimaginable depth now lingered. These were the first black holes, the silent remnants of titanic stars, each one a gravity well so deep that not even light could climb out. In a way, they were the shadows of those lost giants, the titans of the early cosmos now gone. All that remained was an invisible imprint of their mass, a region of space turned utterly black. To an outside observer, a black hole is a sphere of darkness, its boundary called an event horizon. Nothing that crosses this boundary ever returns. It is a one-way door into the unknown. In the vicinity of a black hole, gravity reigns supreme. Space itself is curved steeply inward, like a funnel without end. If you drifted near, you would feel its pull growing stronger with every passing moment. Time would seem to slow down as you approached the edge, and to a distant observer, you might appear almost frozen at the brink. But you would feel nothing extraordinary as you crossed the event horizon, only the point of no return silently passing. Beyond that horizon, the very concept of where and when begins to lose meaning. What lies inside, at the black hole's heart, is hidden from the universe behind a curtain of night. The early universe soon had many such shadows scattered among the first galaxies. Some were small, born from a single collapsing star and containing a few times the sun's mass. Others grew more ambitious. In regions rich with gas, a black hole could gorge itself, swallowing material from its surroundings and swelling in mass. When a black hole feeds, the infalling gas spirals into it, heating up and glowing fiercely just before crossing into darkness. For a while, the area around the black hole can blaze brighter than an entire galaxy, powered by the matter funneling into the void. These brilliant beacons are quasars, among the brightest lights in the young universe, ironically fueled by the darkest of objects. Not even a billion years after the Big Bang, quasars shone from the hearts of growing galaxies. They signaled that some black holes had already become monstrous, reaching millions or even billions of solar masses. How they grew so quickly is a mystery that puzzles scientists to this day. Perhaps smaller black holes merged together, or huge clouds of gas collapsed directly to form massive black holes in one go. Whatever the path, by the time the universe was a toddler in cosmic terms, giant black holes, true titans in their own right, anchored the centers of forming galaxies. Around them, swirls of stars and gas rotated, caught in the grip of gravity's maestro. Each galaxy likely harbored a central black hole, quietly shaping its fate. Through bursts of energy and gravity, these central black holes could regulate how stars formed in their vicinity. When a black hole feeds voraciously, it can drive fierce winds of ionized gas outward, blowing bubbles in galaxies and even shutting down star formation for a time. In gentler times, the black hole slumbers and the galaxy grows undisturbed. This cosmic push and pull between a galaxy and its hidden heart would continue for eons, subtly influencing the size and shape of galaxies that we see today. Black holes themselves emit no light, but they can create spectacular light shows through their effects. Sometimes, two galaxies would draw close and merge, their stars and gas intermingling in a slow dance. If each galaxy carried a central black hole, eventually those two black holes would drift toward each other, spiraling closer in the quiet dark. For a long while they circle, an unseen duet in the center of a chaos of colliding stars. When finally they collide and merge, they do so invisibly, but not silently. The fabric of space trembles from the impact, sending out ripples that travel across the universe. These ripples in space-time are gravitational waves, a gentle ringing of the cosmos, like a distant gong struck ages ago. Such events were rare and hidden behind veils of dust and distance. For nearly the entirety of cosmic history, the waves from merging black holes went unnoticed, dissipating their energy across the eons. But they carry with them a record of those dramatic moments. And one day, intelligent life on a small blue planet would build instruments to detect this faint chorus. In recent times, we have begun to hear the universe for the first time, catching the whisper of black holes merging billions of years ago. It is as if gravity had been singing in secret all this time. And at last, we have the ears to listen. This new way of sensing the cosmos opened yet another window into the unseen. The final verses of gravity's song, long predicted, but only now observed. To imagine a black hole up close is to confront extremes. The gravity is so intense that it warps light into rings and arcs around it, creating a visual halo around the darkness. Beyond the horizon, space falls inward, and at the core, all our understanding of physics breaks down in what is called a singularity, a point of infinite density. It is a place of mystery that no probe or signal can ever report back from. Black holes thus remain one of the universe's most profound enigmas. We know they exist. We can describe their properties. Yet what lies inside remains beyond our reach. They are both destructive and creative, swallowing stars even as they trigger new star formation through their influence, sculpting galaxies while hiding silently at their centers. They remind us that even in an era of light, darkness has its active role to play. The emergence of black holes marked a new chapter in the cosmic story. From the remnants of dying giants came objects that challenge imagination. In the early universe, these black holes were points of intense gravity around which matter orbited and sometimes blazed. They were the seeds of galaxies and the agents of both destruction and creation. As the universe continued to evolve, countless black holes, large and small, took their places in the cosmic tapestry. Each one is like a silent bell, ready to toll if disturbed by a collision or a feast of matter. Silent, yet capable of sending vibrations across space and time. Through black holes, we see that the universe's darkest mysteries often lie at the heart of its brightest wonders. The universe had passed through its long night and into a bright, bustling day. Billions of years after the first stars flickered to life, the cosmos was filled with galaxies of every shape and size. Gravity continued its creative work, pulling together clouds of stars into grand assemblies. Spiral galaxies unfurled like cosmic roses, their arms glittering with countless suns. Elliptical galaxies formed as smaller ones merged, great swarms of stars held together in spherical halos. Everywhere, galaxies clustered into families, groups and clusters bound by their mutual pull, connected by the fine threads of the cosmic web. What was once a nearly uniform expanse had evolved into a complex tapestry of light and structure. With the universe truly awake, new wonders emerged on smaller scales as well. In the spiral arms of galaxies, dense clouds of gas and dust gathered and gave birth to new stars in vast stellar nurseries. Around many of these stars, disks of leftover dust coalesced into planets. Some worlds were barren rock and ice, others gas giants with swirling storms. On at least one small rocky planet, circling a star in the outer reaches of a quiet spiral galaxy, the ingredients forged in ancient supernova assembled into something astonishing. On that world, life sparked into being. Over eons, it grew more complex, until one day, creatures on that planet began to look up and wonder at the stars from which they came. Indeed, the atoms of our bodies were born in stars and scattered by their deaths. We are a way for the cosmos to know itself, an awakening within the grand cosmic dawn. As humans gaze into the night, we are seeing our own ancient origins. The light reaching our eyes from distant stars and galaxies set out long before Earth even existed, and the gentle glow of the cosmic microwave background that pervades the sky is a relic of a time before any star had ever shone. In a very real sense, when we peer into space, we are looking back in time, witnessing the universe awakening across the ages. Gravity's song, the ceaseless pull that orchestrated the universe's growth, can be heard in the patterns we observe today. It is evident in the graceful dance of galaxies around one another, and in the orbits of stars swaying to the gravity of their galactic centers. It sounds in the faint ripples of space-time from ancient collisions, and in the steady rotation of planets about their suns. Every structure, from the majestic galaxy clusters to the rings of Saturn, moves to gravity's subtle music. It is a quiet music, one that we feel more than hear, but it has guided the cosmos from its infancy to its present splendor. The universe continues to expand, carrying galaxies ever farther apart, like a swelling symphony reaching into silence. The same expansion that began with the Big Bang still persists, and in fact is accelerating due to a mysterious influence we call dark energy, which we have yet to fully understand. Through it all, stars live and die, galaxies collide and settle, and new wonders take shape. Yet even as distances grow, the cosmos remains interconnected by the primordial threads of gravity and by the light that travels across the darkness. We find ourselves at a time when the universe is vibrant with activity, a cosmic midday, billions of years after the dawn, with countless stars shining in the expanse. Now, as we lie under the canopy of the night sky, we can appreciate the journey that brought us here. The soft starlight that soothes us has travelled vast distances and times to reach our eyes. Every whisper of wind, every breath we take, contains atoms once forged in stellar furnaces. We are children of this cosmos, cradled by the Milky Way, which is itself one galaxy among trillions. The lullaby of the cosmos still plays in the background, the faint microwave glow from the universe's infancy, joined now by the gentle chorus of billions of stars. It is a song of serenity and wonder, a reminder of our connection to the grand tapestry of existence. The story of the universe is far from over. In the great expanse of time, stars will continue to be born and to fade away. Galaxies will drift and dance, and space will keep stretching outward. New mysteries will surely arise as we probe deeper into the cosmos. We stand at the shore of a cosmic ocean with much left to explore and understand. Yet, after witnessing the journey from darkness to light, we can rest in the knowledge that we are part of this magnificent unfolding. The cosmos holds its secrets patiently, revealing them piece by piece to those who listen to its quiet tunes. For now, we gently close this chapter of our exploration. Above us, the stars still shimmer with ancient light, singing the lullaby that began so long ago. The universe has awakened from its slumber, filled with light, life, and endless wonder. As we drift into our own quiet rest under the same cosmic sky, we carry with us the calm of knowing how the darkness blossomed into day. When we return to continue this journey, more marvels and mysteries will await among the stars. Until then, the darkness and the wonder remain, ever present, ever inviting us to dream of the worlds and secrets yet to be discovered. Beyond the warm glow of our familiar sun and the twinkling tapestry of distant stars, a deep darkness beckons. We venture outward, leaving behind the comfort of the known. The blue glow of our home world fades away, until Earth is just a memory against the black. Even our sun shrinks to a bright point of light among many, its warmth now far behind us. In the silent cosmic ocean ahead, light grows scarce. Our vessel of imagination drifts into an expanse of almost perfect night. Here, in the quiet of interstellar space, we sense a presence, a pull, gentle but insistent, drawing us further into the abyss. Stars thin out as we travel farther from home. The Milky Way's bright band, once a river of light across the sky, begins to fade. We are heading toward a region almost empty, yet not truly void. Invisible to our eyes, a massive gravity well is tugging at stray stars and wayward clouds of gas. It is a black hole, an object of such overwhelming density that its gravity ensnares anything that strays too close. Not even light can escape its grasp. We approach this cosmic abyss with reverence and wonder. There are no familiar landmarks here, no nearby planets or glowing nebulae, only the endless night and the subtle tug guiding us in. Imagine floating in this darkness. No up or down, no day or night, only the distant shimmer of galaxies far behind us. The black hole itself remains unseen. We know it is there only by the way it warps the path of light around it, and by the growing sense of gravity's pull as we draw nearer. Ahead, a delicate glow begins to emerge against the darkness. It is not the black hole we see, but the matter caught in its influence. Dust and gas from ancient stars have gathered and swirl in a broad disk, heated to a gentle radiance as they spiral inward. This halo forms an accretion disk, a final ring of light circling the void, a cosmic whirlpool glowing as it falls toward oblivion. It shines softly, a lonely ember in the darkness, whispering the presence of the invisible giant at its center. Against that faint glow, the black hole announces itself. In fact, humanity has managed to glimpse such a scene in reality. Not long ago, astronomers joined telescopes around the globe to capture the silhouette of a black hole in a distant galaxy. They saw a hazy, circular glow, light from an accretion disk, framing an eerie round shadow. It was the unmistakable imprint of a colossal black hole, a sight once thought impossible. A glowing ring around a void, frozen in a distant moment, confirming that these enigmatic giants are out there, shaping the cosmos. As we drift closer, the pull of gravity intensifies. We feel an eerie calm as there is no resistance in the vacuum, yet our speed increases, drawn by an unseen hand. The black hole's gravity dominates this region, sculpting space around it. Starlight passing near the hole is bent and reshaped, forced to curve around the darkness. We begin to see strange distortions. The stars behind the black hole appear smeared into arcs of light. Space itself seems to ripple with mirages. This gravitational lensing creates a visual halo, as if space is a crystal lens and the black hole the lens maker, bending the cosmos to reveal its presence. It is as if space itself is bowed inward here, a deep well in the fabric of reality. We are descending into that well, drawn toward a place where the usual rules of nature begin to blur. Down and forward lose their meaning. All paths lead toward the center. The closer we get, the more that space and time themselves are stretched and warped by the black hole's mass. It is a gentle descent from our perspective, peaceful and silent, yet we know the forces at play are unimaginably powerful. Time itself behaves differently near this massive emptiness. Far from the black hole, clocks tick normally, aligned with our intuitive sense of time. But here, in the grip of intense gravity, time dilates and stretches. Each second for us holds more than a second would for someone far away. If we could see a clock back on Earth, we'd perceive its hands spinning faster relative to our own slow time. What might be hours for us could be years for an outside observer watching our approach. We are on the threshold of a region where time and space trade their ordinary roles for something much stranger. Now the dim halo of the accretion disk thins out, and ahead of us yawns a deeper blackness. We have reached the edge of the ultimate frontier, the event horizon, the point of no return. This boundary is invisible yet absolute. It is a spherical veil drawn around the black hole, defining where the inward pull becomes irresistible. On one side of this boundary, it is possible to escape if one has enough speed or energy. On the other side, no force in the universe can break free, not even light. We do not see the event horizon as a solid surface. It is simply the region where the starry backdrop and the glow of the disk vanish into a perfect dark. Crossing that threshold would mean leaving the observable universe behind, slipping into a realm from which no message can be sent back. As we approach this boundary, something peculiar happens from the viewpoint of the wider universe. Our ship, which moved swiftly through normal space, now appears to an outside observer to slow down as it nears the horizon. It is not an illusion, but a consequence of warped time. To distant eyes, our descent stretches into eternity. Our form would dim and redden as the light we emit fights to climb out of the gravity well. Eventually, to those afar, we would seem almost frozen at the brink, our final image fading slowly, never quite vanishing, trapped just outside the edge of darkness. Yet here on our ship, time feels unchanged. Moments pass naturally for us as we continue to drift forward. We notice no abrupt wall or barrier at the event horizon. The crossing, from our perspective, would be silent and uneventful. Ahead, there is only blackness. Behind us, the universe we left grows faint and unreachable. We pause in this moment, as if standing on the shore of a vast, dark sea, aware that just a few more steps will carry us into waters from which we cannot return. In this pause, we reflect on what lies before and behind. This black hole may have once been a giant star that exhausted its life and collapsed under its own weight, punching a hole in the fabric of the cosmos. Or perhaps it is one of the primordial black holes, born in the early universe, though those remain speculative. It could even be a supermassive monster anchoring the heart of a galaxy, millions or billions of times the mass of our sun, a dark engine around which stars and nebulae orbit. Whatever its origin, it is a place of both endings and mysteries, matter and light that venture too close are lost to us, and the known laws of physics themselves falter within. Floating at the very edge of the horizon we sense a profound stillness. The turmoil of the accretion disk, its heat and radiation, is mostly behind us now, above and around us. Here, right at the brink, there is an eerie calm. Any light from the outside universe is now feeble and red-shifted, struggling to reach us through gravity's filter. We are in a deep shadow, a quiet zone between the starlit universe and the abyss. It is a solitude unlike any other, poised at the border of the ultimate unknown. The black hole's pull remains relentless and uncompromising. Were we here in reality, our fate would already be sealed. Gravity would begin to stretch us lengthwise, tugging harder at our feet than our head if we approached feet first. This difference in force is small when far away, but close to the black hole it grows immense. The result is a phenomenon poetically named spaghettification. Any object, be it a spaceship or a human body, would be stretched into a long strand by these tidal forces. In a smaller black hole, this stretching would tear us apart long before we ever reach the horizon. In the case of a supermassive black hole, the tidal forces at the horizon might be mild enough that one could slip across without immediate harm, only to be destroyed nearer to the core. Either way, the journey ends in the same ultimate destination, the central singularity, where matter is crushed to unimaginable density and the known laws of nature break down. We linger at the threshold a moment longer, contemplating the strange nature of this boundary. Concepts of inside and outside lose their usual meaning here. The event horizon is a one-way surface, a cosmic trapdoor. We can enter, but we cannot exit. No signal, no light, no information of any kind can cross back once past this point. This is a frontier, not just of space, but of knowledge. What lies beyond it is hidden from the rest of the universe. Does time itself come to an end at the singularity deep inside? Or could there be a bridge to somewhere else, perhaps another universe entirely? Such questions arise naturally in this place, yet they hang unanswered in the stillness. The true interior of a black hole remains one of the universe's best-kept secrets. With calm determination, we prepare to cross the horizon in our thought experiment journey, knowing it is an imagined voyage no real spacecraft could yet dare. As we slip over this cosmic brink, the outside universe disappears from view in an instant. We are enveloped in an almost perfect darkness. The moment of crossing brings no fanfare, no jolt. One instant we see the faint glow of the outside, and the next we are in the black hole's embrace. We have entered a realm cut off from the rest of existence. Inside, we drift in silence deeper toward the core. We try to comprehend what surrounds us, but without light or signals from outside, there is only the inexorable pull inward. The gravity here guides everything toward the center. Space itself funnels down like a river, narrowing to a point. In our mind's eye, we imagine the singularity at the very heart of this black hole, a point where all the mass has been crushed down to an infinitesimal scale. It is a place we cannot truly picture, a point of infinite density and zero volume, where the normal fabric of space and time is contorted beyond recognition. Here our journey meets the limits of understanding. The physics we rely on can no longer chart a course. And so, at this brink of the unknowable, we pause our descent. In truth, to go further is to enter a realm we are not yet able to describe or imagine fully. We have journeyed to the abyss and touched the edge of a great mystery. In our thoughts, we hold this experience, feeling the tug of the darkest gravity, seeing the warping of starlight, and crossing the silent boundary that divides what is seen from what is forever hidden. Rather than plunge to destruction, we choose to linger here in a silent equilibrium, balanced between the known universe and the black hole's domain. From this unique vantage, our attention turns outward again. We slowly drift back from the event horizon, making our way to the space outside the black hole's grip. The universe we left gradually brightens and comes back into view. Stars reappear. Light fills our surroundings once more. We carry with us a profound reverence for what we have witnessed. And as we emerge from the shadow of the black hole, we become aware that the silence around us is not absolute. The black hole, for all its consuming darkness, has other ways of making itself known. In the gentle return to the starlit vastness, we notice a faint vibration in the fabric of space, a ripple passing through, so subtle that it could easily be missed. It is as though the cosmos has been holding its breath, and we have caught the quiet aftermath of a distant cosmic chord. This is the universe's silent music, gravitational waves. When massive objects like black holes move or collide, they send out ripples through space-time itself. These ripples are the faint tremors we now sense, a symphony of silence that can travel across the cosmos. We have left the immediate vicinity of the black hole, but we are still connected to it by these ghostly echoes of its presence. The darkness is not silent after all. It carries the memory of violent events in waves that wash over us like the gentlest of tides. We are witnessing the faint aftermath of a colossal event that took place eons ago. Somewhere in the vast darkness, two massive bodies, perhaps black holes or neutron stars, spiraled together in a cataclysmic dance. When they collided, space itself shuddered and rang like a cosmic bell. The vibrations of that moment have been travelling outward ever since, spreading across the universe. Now, like a pebble's ripples reaching a distant shore, these gravitational waves wash over us, letting us momentarily sense that faraway upheaval. Gravitational waves are unlike any other phenomenon we know. They carry no light, no colour, and they move through the universe without a sound. Instead, they are ripples in space-time itself, stretches and squeezes of the very fabric of reality. As one passes by, it subtly alters distances, one moment stretching them apart, the next moment compressing them, all by infinitesimal amounts. If a gravitational wave were to roll through where we float, even our bodies would be stretched in one direction and compressed in another, though by an amount so tiny we would never notice. These waves are nature's quietest whispers, coursing through creation. For most of human history, we had no way to know these whispers existed. They passed through Earth undetected, silent and swift, leaving no trace in our limited senses. Yet, over a century ago, Albert Einstein's equations first hinted at their existence. He imagined space and time as a fabric, and massive objects as weights that could send ripples across this fabric. Still, even Einstein doubted we'd ever measure such waves. They seemed too faint, too elusive. The universe, it seemed, kept this symphony of silence beyond our reach. But human curiosity is tireless. In recent times, we built instruments of astonishing sensitivity to listen for these space-time murmurs. In quiet laboratories, long tunnels with laser beams were constructed to measure impossibly small changes in distance. And then, one day, they heard a faint, distinct signal. It was a rising tone, a brief chirp when converted into sound, the telltale signature of two black holes merging in the depths of space. After billions of years of traveling outward, the gravitational waves from that distant merger had finally arrived at Earth, and our instruments caught that subtle distortion. For the first time, we had heard the cosmos speak in the language of gravity. That first detection opened a new chapter in our exploration of the universe. We learned that the cosmos has its own form of music, and we had begun to tune in. Since then, dozens of gravitational wave events have been recorded. We have heard the collisions of other black holes, the deep thrumming bass of neutron stars spiraling together, even the rumbling crash when two neutron stars collided and shook both space and time. Each event comes as a faint melody from the stars, carrying information about things we could never see with light alone. Through gravitational waves, we know now that black holes often exist in pairs, orbiting one another in a fateful waltz. We know that when neutron stars merge, they create explosions that forge heavy elements like gold and platinum, enriching the cosmos. All this knowledge arrived encoded in those quiet ripples, decoded patiently by scientists listening to the void. Indeed, even when no single event stands out, the universe is filled with a background hum of gravitational waves. Like the murmur of many conversations in a crowded room, countless distant collisions and mergers over the history of the universe create a constant gravitational whisper in the cosmos. Recently, astronomers have found hints of this background hum by carefully studying radio pulses from neutron stars called pulsars. The rhythm of those pulsars arrives on Earth just slightly perturbed, as if jostled by the subtle waves passing between the stars. It appears the universe has been humming a deep, ancient tune all around us, all along. We are only now becoming aware of this cosmic background music. Floating here in space, far from any planet or noise, we imagine we can almost feel the faint trembling of that universal harmony. It is tranquil and wondrous to think about. The very emptiness around us is alive with ghostly vibrations from events millions or billions of light years away. Each wave that passes is a messenger carrying the story of a distant cosmic drama, the collapse of a star, or the merger of black holes in a galaxy we will never see. They bring no light or heat, only a distortion of space itself that whispers, "Something remarkable happened here." Gravitational waves have given us a new sense, a way to perceive the invisible. Through them, we now listen to the dark side of the universe. Where telescopes see darkness, gravitational waves can reveal motion and upheaval. They confirm that even in events hidden from light, like two black holes merging in total darkness, there is a way for us to know they occurred. The silent symphony becomes our guide to phenomena that were once mere imagination. With each new detection, we expand our understanding and our connection to the cosmos. As we absorb the significance of this silent music, our journey carries us onward. Drawn by curiosity, we decide to follow one of these gravitational melodies to its source. Among the many waves washing over us, we focus on a particular signal, a simple rising tone in space-time, like the last few notes of a universal song. It is the final tremor from a monumental event, two black holes that have collided and merged into one. Let us trace this wave backward to witness the dance that produced such a profound ripple in the cosmic sea. We let the gentle gravitational wave guide us backward to its origin. In our mind's eye, we travel to a distant galaxy, to a time long ago. Here, two black holes are locked in an intimate orbit around each other. Each one is a titan in its own right, perhaps 30 times the mass of our sun, born from the remnants of massive stars that lived and died together. Now these two dark giants circle a common center, engaged in a gravitational dance that has lasted for eons. In the beginning, their orbit was wide and leisurely, but as millennia passed, they drew closer. Slowly, inexorably, they spiral toward each other, their motion tracing a fate set by gravity. We observe them from a safe distance in space, where their immense gravity will not trap us. At first, the black holes move in a slow waltz, taking many seconds to complete a single orbit. They are invisible against the darkness, with no light of their own, but we sense their presence by the way background starlight warps and blurs around them. As time accelerates in our narrative view, we see the dance quicken. The black holes circle faster now. What once took hours now takes moments. With each revolution, they shed a bit of orbital energy, broadcasting it away as gravitational waves. Those waves carry the news of their dance out into the cosmos, and the black holes draw ever closer in response. The final moments of this cosmic dance are breathtaking and violent, though played out in silence. By now, the two black holes are orbiting dozens of times every second, whirling around each other at a significant fraction of the speed of light. They are so close that only a few hundred kilometers separate their event horizons. Space around them churns like water in a whirlpool. If we could somehow see gravitational waves, we would witness space itself rippling outward in concentric rings, growing stronger as the inevitable collision nears. Each fraction of a second, the frequency of their orbit increases, a rising trill in the gravitational song they are sending across the universe. Finally, the two black holes meet. In one last orbit, they close the gap and collide, merging into a single, larger black hole. The moment of coalescence is the grand finale of their dance. An enormous amount of energy is released in this instant, not as a flash of light or fire, but purely as a pulse of gravitational waves. The fabric of space-time quivers from the impact. In the briefest blink of cosmic time, the equivalent of several suns' worth of mass is converted into a burst of gravitational energy. For that fleeting moment, this merging black hole outshines entire galaxies. Yet all of its brilliance is in those invisible waves racing out in all directions. The newly formed black hole rings like a struck drum. It is slightly distorted from the tumult of merger, and as it settles into a perfect sphere, it emits a few final diminishing waves. This is called the ring down, the last tiny tremors of vibration as order is restored. Soon, the single merged black hole is calm and still, aside from its silent rotation. No light marks this moment. To any distant observer with a telescope, nothing visible betrays what has happened. Only the departing gravitational waves carry the tale. These waves travel outward at the speed of light, spreading into the universe. As they expand, their intensity diminishes, yet they continue on, unstoppable. In time, after journeying across millions or even billions of light years, they will reach far-flung corners of the cosmos. Perhaps one day, a planet orbiting a distant star will briefly quiver under their passage. Much later, on a small blue world we know, sensitive instruments will stir ever so slightly, bearing witness to the ancient collision. But at the source, all has gone quiet. We remain for a moment near this newly born solitary black hole. In the immediate aftermath of the merger, the violence is over. Where once there were two, now there is one. The giant black hole carries on through space, perhaps with a slight recoil kick from the asymmetry of the collision, drifting toward a new orbit within its galaxy. The drama of the merger fades into memory. What remains is a bigger black hole, rotating and dark, gradually swallowing any residual matter that might wander nearby. Not all cosmic collisions are as silent as this one. If the dancers were neutron stars instead of black holes, their merger would have unleashed a spectacular explosion of light and high-energy radiation, along with gravitational waves. Such an event would briefly outshine an entire galaxy and scatter elements into space. But our two black holes produced no such fireworks. Only the silent gravitational chorus marked their passing. This is why, until we learned to listen to gravitational waves, these events were invisible to us. Black hole mergers are like a secret dance in the dark, their grand finale hidden from view, except for the space-time echoes we have now learned to detect. The dance of these titans is over, but it has left an imprint on the universe. The gravitational waves from their merger continue to spread, a lasting memory of the event. In our journey, we followed those waves to witness the collision. Now, having seen it up close in our imagination, we can appreciate the remarkable power and subtlety of such cosmic transformations. Two mighty black holes became one, releasing energy beyond comprehension in the process, yet doing so in utter darkness and silence. As we prepare to leave this scene, our perspective shifts. We drift away from the merged black hole, letting the distance between us grow. The galaxy around us comes back into view. Millions of stars, nebulae, and perhaps other black holes lie scattered throughout. The universe is full of such dances and collisions, though they occur on timescales far beyond human lives. We have been privileged to witness one in accelerated time. In the quiet that follows, we reflect on what we have observed. Massive black holes can collide and send ripples through reality itself. We have essentially watched space-time ring like a cosmic gong. Yet there is more to the story of black holes than these powerful mergers. Black holes have another, more subtle way of interacting with the universe, a side of their nature that unfolds not in a sudden cataclysm, but slowly, over eons. Even as this newly merged black hole now silently floats in the darkness, it will, ever so gradually, begin to lose energy in the form of an almost imperceptible radiation. In effect, it will very slowly evaporate, fading away, bit by bit, over unimaginable spans of time. To explore this gentle whisper from a black hole, we turn to the insights of a great mind from our own planet. It was Stephen Hawking who first proposed that black holes are not completely black, that they can emit a faint, ghostly glow. This idea was radical, tying together the laws of quantum physics and gravity in a startling way. Now, leaving behind the spectacle of colliding giants, we shift our attention to Hawking's quiet revelation and the quantum secrets it suggests. Our journey now turns to the subtle phenomenon that Stephen Hawking predicted. A phenomenon so gentle that, for a black hole born of collapsing stars or colliding giants, it is completely overwhelmed by every other cosmic noise. Yet over inconceivable spans of time, it becomes the dominant process. This is Hawking radiation, the quiet whisper of a black hole. Imagine we could watch our newly merged black hole not for years or centuries, but for trillions upon trillions of years. At first, nothing noticeable happens. The black hole simply exists, dark and unchanging against the starry background. But Hawking's theory tells us that, even now, an incredibly faint energy is leaking from its event horizon. To understand this, we need to delve into the strange world of quantum physics that operates on the smallest scales. In empty space, according to quantum theory, particles and their antiparticles are constantly flickering into and out of existence. They appear as a pair and then quickly annihilate each other, typically gone before they can be observed. This happens everywhere, all the time, even right at the edge of a black hole's event horizon. Hawking realized that if such a pair of virtual particles forms just at the horizon, one of the pair could fall into the black hole, while the other escapes before they have a chance to destroy each other. When this happens, the escaping particle becomes real, carrying away a tiny bit of energy. The particle that fell in, effectively, has negative energy, relative to the outside, and thus reduces the black hole's total energy. To put it another way, the black hole loses a small fragment of its mass to pay for the energy that the escaping particle carries off. To an outside observer, the black hole seems to be emitting particles, a very faint glow against the cold of space. This glow is unimaginably weak for a black hole of any substantial size. If the black hole is as massive as our Sun, the temperature of its Hawking radiation would be only a few billionths of a degree above absolute zero. Even the glow of the cosmic microwave background, the afterglow of the Big Bang at about 2.7 degrees above absolute zero, utterly drowns out such a feeble signal. For a black hole weighing as much as a star, Hawking radiation is essentially impossible to detect with any foreseeable technology. It is truly a whisper in the dark. Only if a black hole were extremely small would its Hawking glow become noticeable. In fact, the smaller a black hole is, the hotter and more intense its radiation gets. A black hole, the mass of a small asteroid, might radiate at around room temperature, and a black hole of the mass of a mountain could emit noticeable X-rays and gamma rays. But such small black holes, if any formed in the early universe, would have evaporated by now. All the black holes we know of in the present universe are far too large for us to directly observe their Hawking whispers. Despite its imperceptibility in practice, Hawking radiation is profoundly important. It is our first hint that black holes are not eternal. Given enough time, they can completely evaporate. The lifespan of a black hole from Hawking evaporation depends on its size. For a typical stellar mass black hole, the evaporation time is mind-bogglingly long, far longer than the current age of the universe. Yet, in principle, given about 1067 years, even a black hole of the Sun's mass would eventually disappear in a final burst of light. Larger black holes, like those lurking in galactic centers, would last even longer, perhaps 100 years or more. Still, the key realization is that black holes are not absolute endpoints for matter. They can give back some of what they took, albeit incredibly slowly. Hawking's insights stitched together the realm of the very small, quantum mechanics, with the realm of the very massive, general relativity. By showing that black holes have a temperature and emit radiation, Hawking essentially gave black holes an entropy and placed them within the framework of thermodynamics. Decades earlier, physicist Jacob Bekenstein had conjectured that a black hole's entropy, a measure of the information and disorder it contains, is proportional to the area of its event horizon. Hawking's calculations supported this bold idea. It turned out that the surface area of the event horizon relates to how much information the black hole could be hiding inside. It is as if the horizon's area encodes, in scrambled form, everything that has fallen into the black hole. This realization leads to one of the deepest puzzles in modern physics: the black hole information paradox. Under the normal laws of quantum physics, information about a physical system, the distinct properties of particles and energy, cannot be destroyed. When something burns, for example, its information isn't lost. It's carried away by the smoke, heat, and light. In principle, if one had perfect knowledge, one could reconstruct the burned object from that information. But if something falls into a black hole, it seems to disappear from our universe entirely. And if the black hole later evaporates away completely, what happens to the information that was inside it? Hawking initially argued that this information is lost forever, essentially erased from existence, because the Hawking radiation leaking out is random and carries no imprint of what fell in. This idea was shocking because it appeared to violate a sacred tenet of quantum theory. For years, a debate raged among physicists. If black holes truly destroy information, then perhaps quantum mechanics itself needs revision. On the other hand, if information is preserved, then there must be some hidden mechanism by which the information escapes the black hole. Today, many scientists suspect that information is indeed not lost. It may be encoded in subtle patterns within the Hawking radiation, or perhaps stored as a kind of hologram on the event horizon, gradually imprinted onto the radiation as the black hole evaporates. Since we have never observed Hawking radiation directly, let alone seen any embedded information, the paradox remains unsolved. Even so, most believe that once we have a complete theory of quantum gravity, one that unites the quantum and cosmic realms, it will show how information finds its way out of a black hole. Stephen Hawking eventually came around to the view that information is likely preserved, and in 2004, he famously conceded a bet he had made on the issue. The exact mechanism for how information escapes a black hole remains unknown, however, and that mystery has spurred a host of new ideas. Some physicists propose that the event horizon might act like a holographic screen, recording everything that falls inside in some form, so that the information isn't truly lost. Others entertain exotic possibilities involving wormholes or quantum entanglement, suggesting that perhaps the interior of a black hole could be subtly connected to the outside world, allowing information to be transferred in unexpected ways. These theories are highly speculative, but they show how Hawking's simple question, what becomes of what falls into a black hole, has led science to the brink of profound new insights. Hawking's revelations have opened a profound mystery, indicating that our existing physical theories may be incomplete. They whisper to us that to truly comprehend black holes, and indeed the universe, we need a new union of ideas, a theory that merges the quantum with the gravitational. In Hawking's work, we hear an invitation to go beyond what is known, to imagine bold new principles that could weave together the fabric of reality. With this thought, we prepare to venture into the realm of the speculative and the fundamental. We have journeyed from the depths of black holes to the subtle quantum whispers at their edges. Now, in the final leg of our cosmic voyage, we will explore the frontier of human knowledge, the dreams of physicists striving to understand the bedrock of existence. From holographic universes to hidden dimensions and quantum gravity, we will drift among ideas as wondrous and mysterious as the cosmos itself, seeking to glimpse the underlying tapestry upon which all these cosmic stories are woven. We drift now into the realm of ideas, where the lines between science and philosophy blur into speculation. Having explored black holes from the epic scale of collisions to the quantum trickle of Hawking radiation, we are left with profound questions. What is the true nature of space and time? What is the ultimate makeup of reality at the smallest scale? In seeking these answers, physicists have spun daring hypotheses, dreams of a deeper understanding that might one day weave gravity and quantum mechanics into a single fabric. One guiding light in these endeavors is the notion of a quantum gravity, a theoretical framework that would describe gravity according to the principles of quantum mechanics. Our current best theory of gravity, Einstein's general relativity, paints gravity as the curvature of space-time caused by mass and energy. This theory excels at describing the grand motions of planets, stars, and the dynamics of the cosmos. Quantum mechanics, on the other hand, is our supremely successful theory for the tiny world of atoms and particles, where probabilities rule and phenomena can occur in discrete jumps. Yet, when we try to apply both theories to something like a black hole singularity or the birth of the universe, situations of extremely high gravity and extremely small scales, the equations break down. The two great pillars of modern physics, so effective in their own domains, seem almost incompatible when brought together. A quantum theory of gravity is the great missing piece, and finding it is perhaps the most ambitious goal of theoretical physics today. What might a quantum theory of gravity look like? One long-standing candidate is string theory. In string theory, the fundamental constituents of reality are imagined not as point particles, but as tiny, vibrating strings of energy. Each mode of vibration corresponds to a different particle. The same string vibrating one way might appear as an electron, and in another mode as a quark or even a graviton, the hypothetical quantum of gravity. Remarkably, string theory inherently includes gravity in its framework and suggests that all forces and particles could be unified as manifestations of one basic kind of object. However, for the mathematics of string theory to work out consistently, it requires additional dimensions of space beyond the three we experience. Instead of our familiar 3D space plus time, string theory posits perhaps 10 or 11 dimensions, with the extra dimensions curled up on themselves in tiny shapes that we don't directly perceive. These hidden dimensions could be all around us, folded into the fabric of every point in our normal space, too small for us to notice, like intricate patterns on a cloth, seen only under magnification. Imagining extra dimensions is difficult, but we can use analogies. Consider how a two-dimensional sheet of paper can be rolled up into a tight cylinder. From far away it looks one-dimensional, just a line, but up close you notice the second dimension curled around. Similarly, space could have unseen loops or cycles. If these extra dimensions are tiny, on the order of the Planck length, about 1.6 by 10⁻35 meters, we wouldn't be able to detect them with current technology. Yet their existence might explain various puzzles and unify forces in a beautiful way. In the calm contemplation of our journey, we entertain the possibility that what we call an elementary particle is actually the resonance of a string vibrating in a higher dimensional space. The complexity and diversity of particles, electrons, photons, quarks, might be like the diverse notes played on fundamental strings. String theory is far from proven. It remains a mathematical construct, albeit an alluring one, and it has not yet made testable predictions that could confirm those extra dimensions or the strings themselves. Some have jokingly called it a dream, because it is so elegant and unifying, yet so far unverified. Whether string theory, or its evolved form known as M-theory, is the right path or not, it has given rise to useful ideas. One such idea is the holographic principle, which emerged from studies of string theory and black holes. The holographic principle suggests that everything that happens inside a volume of space could be described by information encoded on the boundary of that volume, much like a flat hologram can encode a three-dimensional image. This principle was inspired by the realization that a black hole's entropy is proportional to its horizon area, hinting that the information content of a black hole, and by extension perhaps any region of space, might be stored on its two-dimensional surface, rather than within its three-dimensional interior. It's a mind-bending concept. Our three-dimensional universe might in some way be a projection of information written on a distant two-dimensional boundary. In a literal sense, the universe could be holographic. If true, notions of volume and space become emergent phenomena, and the fundamental description of reality might exist on a lower dimensional scaffold. Another bold framework in the pursuit of quantum gravity is loop quantum gravity. Rather than positing strings, loop quantum gravity takes a more conservative route, attempting to quantize space and time directly. In this theory, space is not continuous, but composed of tiny, discrete chunks or atoms of space, woven together in a network of loops, hence the name. The smooth space-time of Einstein's theory would then be like a fabric made of these loops, much as a piece of cloth, when viewed up close, is a grid of woven threads. Near the Planck scale, this network becomes apparent, and phenomena like singularities might be resolved because you can't squeeze space smaller than its fundamental units. Loop quantum gravity predicts that volumes and areas come in discrete quanta. It hasn't yet reached the same level of unified description of all forces as string theory aims to do, but it offers an intriguing glimpse of a possible quantum structure underlying space-time itself. Both string theory and loop quantum gravity, and other approaches as well, strive to describe a fabric of reality that is deeper than our everyday experience. In these visions, space and time are not immutable, infinitely divisible backdrops, but emergent or made of something more fundamental. If we think of space-time as a tapestry, these theories suggest that at ultra-small scales, we will find threads, be they strings, loops, or some other entities, whose weaving pattern gives rise to the illusion of a continuum. What would it be like to actually see this deep layer of reality? If we were to shrink down to the Planck length, the universe might appear incredibly chaotic and frothy. John Wheeler, a physicist, coined the term quantum foam to describe how space and time might behave at such scales. Fleeting particles and tiny black holes could be appearing and disappearing constantly, warping geometry in rapid, unpredictable ways. The smooth flow of time we perceive might dissolve into a jittery uncertainty, and distances might lose clear meaning. In this view, the fabric of reality is restless and ceaselessly creative at its lowest level, a stark contrast to the calm, continuous space-time we move through in daily life. In fact, such quantum chaos may have reigned in the earliest moments of our universe. When the cosmos was incredibly hot and dense, perhaps compressed to a size smaller than an atom, space and time themselves would have been subject to wild quantum fluctuations. Our current physics breaks down in that primeval era. The Big Bang remains an event cloaked in mystery. But a successful theory of quantum gravity could peel back that veil, showing how a smooth, expanding universe emerged from a froth of quantum uncertainty. It would bridge the gap from the Planck scale tumult to the vast cosmic structure we see today. Beyond questions of quantum gravity, physicists also entertain the possibility that our reality is just one part of a much grander existence. Some propose a multiverse. Perhaps there are countless other universes, each with different physical constants, or even entirely different laws, born in a vast inflationary space beyond our observable horizons. Alternatively, the multiverse might arise from quantum mechanics, the many worlds. Interpretation suggests that every quantum event that has multiple outcomes actually spawns separate branches of reality for each outcome, each as real as our own, but forever inaccessible to one another. As fantastic as this multiverse notion is, it remains speculative. We have no direct evidence of other universes, Still, the concept serves to remind us how little we may truly know. The cosmos might be like an endless ocean, and our universe just one droplet within it. While we journey through these speculative landscapes, we remember to keep one foot on firm ground. The mysteries we know to be true, and yet unexplained in our own universe. Consider dark matter, the unseen mass that shapes the rotation of galaxies and the large-scale structure of the cosmos. It outweighs the ordinary matter we observe by roughly 5 to 1, forming a hidden scaffold across space for galaxies to coalesce upon. We can't see this substance, but we detect its gravitational influence everywhere. And dark energy, an even stranger phenomenon, is driving the acceleration of the universe's expansion, as if a hidden force is blowing up space itself. It is as though the vacuum of space has an inherent energy pushing the cosmos outward. This dark energy now dominates the universe's energy balance, yet its essence remains one of the deepest puzzles in physics. These are not mere theoretical musings. They are realities implied by astronomical observations, crying out for understanding. Any complete picture of the fabric of reality must eventually account for these dark components that overwhelm our cosmos. Are they made of unknown particles? Do they hint at new fields or principles? Or are they telling us that our theories of gravity and cosmology need revision on the larger scales? We do not yet know. Our contemplation of quantum dreams and fundamental mysteries brings us to the edge of the known world and into the unknown. Here, at the conclusion of this part of our journey, we feel a serene openness to whatever secrets the universe holds. The night sky above, or rather, the fabric of reality beneath, is vast and full of wonder. We have traversed the realms of black holes and quantum conundrums, and each revelation has pointed to even deeper questions. There is a gentle continuity to our exploration. As we leave the domain of black holes and quantum speculation, we set our sights on those other grand enigmas that await. The invisible matter that binds galaxies, the mysterious energy swelling the expansion of space. These dark wonders beckon us onward. Without fanfare or finality, we carry our curiosity forward into the next chapter of discovery. The cosmos stretches out before us, dark and beautiful, and we drift onward, ready to embrace the mysteries that lie ahead. In the darkness between the stars, a quiet mystery unfolds. After all the brilliant cosmic wonders we have seen, we now drift into the realm of the invisible. There is a hidden presence enveloping the galaxies, an unseen influence guiding their dance. It is often called dark matter, shadow matter that neither shines nor casts any light of its own. We cannot see it, yet its gravity sculpts the universe, holding each galaxy in a gentle but firm embrace. Imagine gazing at a spiral galaxy twirling in the void. Its luminous arms are sprinkled with billions of stars, glowing softly like distant lanterns in the cosmic night. But far beyond this starlight, something else is there. Stars at the galaxy's edge whirl faster than they should, as if grasped by an immense, invisible halo. Decades ago, an astronomer named Vera Rubin noticed this cosmic oddity. She found that the outer stars were orbiting swiftly, defying the expectations set by the visible matter alone. It was as though an enormous hidden mass was pulling at them, preventing these stars from drifting away into space. This invisible mass revealed itself as dark matter. Its existence had been suspected even earlier. Back in the 1930s, Fritz Zwicky studied far-off clusters of galaxies and observed a similar mystery. the galaxies in those clusters moved as if bound by far more mass than anyone could see. Something abundant and unseen was holding them together, like a cosmic glue. Rubin's work decades later confirmed it. The universe contains far more matter than the stars and gas we can directly observe. For every shining star or glowing nebula, there appears to be an enormous quantity of dark matter surrounding it, outweighing the visible matter many times over. Dark matter's influence extends beyond the motions of stars. We can literally see its effects by how it warps light on a cosmic scale. When we observe a massive cluster of galaxies, we often find that the light from even more distant galaxies behind it is bent and smeared, as if by a gigantic lens. This phenomenon, known as gravitational lensing, is gravity's way of bending light. The amount of bending is a telltale sign of mass. In many cases, the visible material in a galaxy cluster, its stars and hot gas, cannot account for the degree of lensing observed. The only explanation is a vast halo of invisible mass enveloping the cluster, magnifying and distorting the light from objects beyond. A dramatic example came from observing a pair of colliding galaxy clusters called the Bullet Cluster. In that cosmic collision, telescopes captured X-ray images of the hot gas, the normal matter, sloshing aside, while maps of gravitational lensing showed the bulk of the mass sailing through seemingly unaffected. The normal matter and the gravity-bending mass had become separated. This was clear evidence that a large portion of each cluster's mass was in an unseen form that interacts very weakly with matter, exactly what we expect of dark matter. Such observations provide direct, visual proof that dark matter is real and behaves as an invisible, collisionless substance governed by gravity. Dark matter is everywhere. It drifts through and around galaxies, including our own Milky Way, forming a vast halo around the visible stars. It does not emit light or heat, and it passes through ordinary atoms without a trace. You could be moving through a sea of dark matter particles right now, without feeling anything. In a sense, it forms a shadow cosmos, an ethereal framework that overlaps the visible universe. We live within this ocean of dark matter, aware of it only by its gravitational tug. Without it, galaxies would fly apart like leaves in a strong wind. Without its unseen pull, the delicate patterns of galaxy clusters and the cosmic web might never have formed as they did. Scientists believe that dark matter provided the scaffold on which the early universe built its galaxies and clusters. Long ago, in the young cosmos, matter of all kinds was spread nearly uniform, with only tiny density variations. Because dark matter interacts little besides through gravity, it began to clump first, drawing together invisibly, while ordinary matter was still held back by radiation pressure. When the universe cooled enough, ordinary gas could fall into those gravity wells that dark matter created, gathering in the same places. There, the gas became concentrated and eventually ignited as the first stars, coalescing into the first galaxies. In this way, dark matter became the invisible scaffolding of cosmic architecture. It is like a hidden lattice or web underlying the visible universe, with galaxies forming along dark matter filaments, like dew, collected on the strands of a vast spider's web. Likewise, computer simulations of cosmic evolution show that without dark matter's gravitational influence, galaxies and clusters would not form as they do. Only by including vast quantities of dark matter do these simulations produce a cosmos that resembles the real one we observe. This adds further confidence that dark matter was essential in sculpting the universe's large-scale structure. Yet for all its influence, the true nature of dark matter remains one of the deepest mysteries in science. We know it only through its gravitational pull, We do not yet know what it is made of at a fundamental level. It might be composed of exotic particles, unlike any that make up the atoms of ordinary matter. Physicists have given some of these hypothetical particles names. WIMPs, for weakly interacting massive particles, and ultralight particles called axions, among others. Even neutrinos, tiny ghost-like particles that are abundant in the cosmos, cannot account for dark matter, because they move too fast to form the structures we see. Dark matter must be something more massive or slower moving. These would have mass and gravity, but interact so feebly with light and normal matter that they are essentially invisible. Ghosts lurking in and around galaxies. Around the world, large detectors deep underground are listening for any whisper of dark matter. Vast tanks of liquid xenon and arrays of ultra-cold crystals have been set up in mines and tunnels, shielded from cosmic rays, hoping to catch a rare collision between a dark matter particle and normal matter. So far, dark matter continues to elude direct detection. Yet the search goes on. New detectors are being developed, and upcoming telescopes, such as the Vera C. Rubin Observatory, named in honor of the pioneering astronomer, will map the cosmos in unprecedented detail, perhaps offering new clues about dark matter's nature. Still, all observations agree that dark matter is there and is essential to the cosmic story. Roughly 85% of all the matter in the universe is dark matter, meaning it outweighs the familiar matter by about 6 to 1. It is humbling to realize that when we look up at the night sky, the glittering stars and glowing galaxies are only a small fraction of what is truly there. Enveloping that starlight is an ocean of dark matter, a vast unseen world interwoven with the visible one. As we float in this quiet cosmic ocean of darkness, we may find a curious comfort. The universe is not chaos. Even in the dark, there is structure and order. Galaxies drift in an invisible gravitational current, moving to the rhythm of an unseen conductor, dark matter's presence. In the grand ballet of the cosmos, this shadow matter provides the baseline harmony, guiding the dance of countless stars without ever revealing itself directly. It is a beautiful thought that so much of the universe's order arises from something we cannot see. It reminds us that reality often extends beyond the limits of our perception, full of truths waiting to be discovered. Our journey into darkness begins with this realization. Much of the cosmos rests on unseen foundations. Yet dark matter is only one facet of the unknown. There is another, even more perplexing form of darkness, a force that does not bind galaxies together, but instead gently pushes the entire universe apart. Like a soft, invisible wind, this dark energy fills the cosmos, steadily stretching the fabric of space farther and farther. For a long time, scientists assumed that the expansion of the universe, set in motion by the Big Bang, was gradually slowing down. Gravity, they believed, would eventually tug on galaxies and slow the cosmic expansion over time. But in the late 20th century, a stunning discovery overturned that assumption. In 1998, two independent teams of astronomers observing distant supernovae, exploding stars used as standard candles, found that those far-off galaxies were dimmer and more distant than expected. The only reasonable explanation was astonishing. The expansion of the universe was not slowing at all. It was speeding up. Before this, many scientists expected gravity to eventually slow or even stop the expansion, perhaps leading to a big crunch contraction in the far future. The 1998 supernova results dashed that expectation, pointing instead toward a universe that will expand faster and faster. Somehow, the cosmos was being pushed outward faster and faster, as if driven by a hidden energy embedded in space itself. This revelation was one of the greatest surprises in modern astronomy. It left scientists both excited and puzzled. To account for it, they dusted off an idea first proposed by Albert Einstein many decades earlier. Early in the 20th century, when Einstein formulated general relativity, he introduced a term in his equations called the cosmological constant, a kind of anti-gravity force, to allow for a static universe, as was then believed. He later removed it, calling it his biggest blunder, after the expansion of the universe was discovered by Edwin Hubble. Yet now, a cosmic repulsion seemed to be manifesting for real. We gave this mysterious influence a name: dark energy. Dark, because we do not yet know what it is. We're in the dark about it. And energy, because it appears to be a property of space that does work on the universe, pushing things apart. The term is a placeholder for our ignorance, a simple name for a profound phenomenon. Unlike dark matter, which clumps around galaxies and clusters, dark energy does not gather in any particular place. It seems to be an inherent property of space itself, uniformly filling every corner of the cosmos. Even the most perfect vacuum, devoid of matter and light, may still contain this energy. One leading idea is that dark energy is the energy of the vacuum, an effect predicted by quantum physics, whereby even empty space seethes with virtual particles and fields. If this vacuum energy is real, then each tiny volume of space carries a minuscule amount of it. By itself, such energy is incredibly subtle and weak, far too small to feel in everyday life or even within a galaxy. But on the scale of the entire universe, all those tiny energies add up, and their collective effect is colossal. Intriguingly, theoretical calculations of vacuum energy from quantum theory overshoot the observed dark energy by an enormous factor, one of the biggest discrepancies in science, meaning we still have much to learn about why dark energy is as gentle as it is. As the universe expands, new space is continuously created, and with it perhaps comes more dark energy. In that way, dark energy does not thin out like matter does. Its density might remain roughly constant as space grows, or at least it declines very slowly. Today, our measurements suggest that about 68% of the universe's total energy content is this dark energy. Roughly 27% is dark matter, and only about 5% is the ordinary matter that makes up stars, planets, and living beings. This was a revolutionary realization. The vast majority of the cosmos is made of these invisible ingredients, with dark energy being the dominant one. The fate of everything we see, galaxies, stars, clusters, is governed largely by something we cannot see. It's humbling to recognize that the universe is driven by a component whose nature we barely grasp. The early skepticism about this cosmic acceleration gradually gave way to acceptance as multiple lines of evidence converged. By the early 2000s, observations of the cosmic microwave background by satellites like WMAP and later Planck confirmed that the universe's energy budget is dominated by dark energy. Cosmologists incorporated this mysterious component into their standard model of the universe, dubbed Lambda CDM. Lambda for the cosmological constant dark energy, and CDM for cold dark matter. In 2011, the scientists who discovered the accelerating expansion were awarded the Nobel Prize in Physics, underscoring how paradigm-shifting this discovery was. Under the influence of dark energy, the large-scale structure of the universe is undergoing a gradual but relentless transition. Galaxies that are not gravitationally bound into groups or clusters are receding from each other at an ever-accelerating rate. As time goes on, distant galaxies will appear to speed away faster and faster. In the far future, If dark energy remains constant, each gravitationally bound region, such as our local group of galaxies, will become an isolated island in an enormous gulf of empty space. Trillions of years from now, an astronomer in our galaxy's far future might see nothing beyond the Milky Way or its merged descendants, because all other galaxies have slipped beyond the visible horizon, their light stretched and dimmed into obscurity. The universe will appear emptier and emptier on the grandest scales. Dark energy, by driving accelerated expansion, is essentially creating cosmic event horizons, boundaries beyond which light from distant objects will never reach us. It ensures that the rich cosmic network of galaxies we observe today will, in time, dissolve into vast solitude, with each local region stranded, virtually alone. To investigate the nature of this mysterious force, scientists have had to be clever, using the universe itself as a laboratory and a time machine. They map the distribution of galaxies, spanning billions of light years, looking for subtle signatures of dark energy's influence in the pattern of how galaxies cluster. They observe more and more distant supernovae to trace how expansion has changed over time, effectively charting the expansion history of the cosmos. They also examine the cosmic microwave background, the faint afterglow of the Big Bang, for clues. Tiny variations in that primordial light encode information about the composition of the universe, including the influence of dark energy. All these methods, remarkably, point to a consistent conclusion. Dark energy behaves very much like Einstein's cosmological constant, an unchanging energy density filling space. If that holds true, it means dark energy will continue to drive acceleration indefinitely, and the universe's expansion will never halt. However, because we do not yet know what dark energy really is, scientists remain open to surprises. Some theories suggest dark energy might slowly change over cosmic time, a dynamic field nicknamed quintessence that could gradually strengthen or weaken. Others have proposed modifications to gravity itself to account for the observations without invoking a new energy. So far, none of these alternative ideas fit the data better than the simplest explanation: a constant dark energy. The discovery of dark energy has added a profound new chapter to our understanding of the cosmos. It underscores that even in what we thought of as empty space, something is at work, something that dominates the universe's evolution. It has transformed our view of the cosmos from one that might cycle or slow down to one that is accelerating toward an ever colder, lonelier state. Yet knowing this also grants us perspective. We happen to live at a time when the universe is still rich with galaxies and light, a time when we can see the cosmic tapestry in all its splendor. Many billions of years hence, observers might not be able to discern what we can today. The evidence of the Big Bang and cosmic expansion will be harder to come by. In that sense, we are fortunate to witness the universe in this era of wonders. Dark energy, mysterious as it is, invites us to appreciate the fleeting cosmos we have now. And it points us onward in our journey, from the forces that shape the cosmos to the spaces that lie in between. Having explored the invisible energy that drives cosmic expansion, we now turn our gaze to the vast stretches of emptiness it creates, the great cosmic voids, where galaxies are scarce and the darkness is deep. In these silent spaces, we will contemplate the nature of nothingness on the grandest scale. The architecture of the universe is defined not only by what is present, but also by what is absent. Between the bright clusters and filaments of galaxies stretch tremendous expanses where almost nothing shines. These are the cosmic voids, enormous regions of space nearly devoid of galaxies, the silent gaps in the cosmic web. Large-scale surveys of the heavens, charting the positions of hundreds of thousands of galaxies, reveal a web-like pattern, filaments and walls of galaxies surrounding immense empty cells. It is a bit like a foam, with the galaxies lining the edges of vast bubbles, and the interiors of those bubbles being great voids. By volume, most of the universe is actually such emptiness. Roughly 80% of the observable cosmos is thought to consist of these void spaces. In other words, the dazzling pattern of galaxies and clusters that we see exists within a much larger framework of almost pure nothingness. Our own cosmic neighborhood offers a hint of this great emptiness. The Milky Way and its companion galaxies float near the edge of a local void, a relatively empty region adjoining our small galactic group. Astronomers refer to this region as the local void, sometimes called the local hole, noting that our galaxy is just at its boundary. Compared to the truly giant voids out in the universe, our local void is modest in size, but it still spans tens of millions of light years with far fewer galaxies than average. Some voids are far larger and emptier. One of the most famous is the Boötes void, an immense spherical region roughly 330 million light-years across that contains almost no galaxies at all. In a volume where thousands of galaxies would ordinarily be expected, astronomers found only a few dozen. So stark is this emptiness that it earned the nickname the Great Nothing. One particularly large void elsewhere in the sky has been conjectured to be responsible for a subtle cold spot observed in the cosmic microwave background, a slightly cooler patch of ancient light. If indeed a supervoid caused this anomaly by imprinting its influence on the travelling light, it would be another example of how even emptiness can leave detectable fingerprints on the cosmos. This idea remains debated, but it shows that the voids, though mostly nothing, are still part of the cosmic story. What would it be like to find oneself in such a place? A galaxy in the heart of a vast void would be an island in an almost infinite night. Its sky would be nearly black, devoid of the usual tapestry of countless galaxies we can see from Earth's vantage. Beyond the stars of its own galaxy, the rest of existence would be practically invisible. A few faint smudges of light at the edge of perception, if any at all. If one lived on a planet in that lonely galaxy and looked out into space, one might not even realize there were other galaxies beyond one's own. The universe would seem to be mostly emptiness, punctuated only by the stars of that one island galaxy. The grand structure we know, the clusters, superclusters, and filaments, would lie beyond the reach of observation. In such a place, the cosmos would feel much smaller and far more desolate. One could gaze into the dark for a lifetime and see only the local stars and maybe a tiny handful of distant galaxies, pale and easily mistaken for faint stars or wisps of cloud. The true enormity and populated nature of the universe would be hidden behind a veil of distance and darkness. These great voids did not start out so empty. In the early universe, matter was distributed more evenly, like a diffuse fog with only slight variations here and there. But as time went on, gravity drew matter into denser clumps, the seeds of galaxies and clusters, and drained it from other regions. The voids grew as the matter that once occupied them was pulled into the surrounding structures. Essentially, where galaxies and clusters formed, they vacuumed up material from their vicinity, leaving behind expanding gaps. Over billions of years, initially modest underdensities became immense cavities. The rich got richer. Dense regions accumulated more matter and became brighter, while the sparse regions lost matter and grew emptier. Today's voids are the spacious cavities left in between the filaments of matter. They continue to widen as the universe expands, and dark energy's accelerating push makes those empty regions grow at an ever-increasing rate. Even so, a void is not truly absolute nothingness. It still contains a tenuous trace of matter, extremely diffuse gas, perhaps a few stray atoms per cubic meter, and the ever-present dark matter that permeates space. Occasionally, a small galaxy or a dim star cluster is found inside a void, isolated like a tiny oasis in a desert. But overall, the density inside a void is far below the cosmic average. If we could stand at the center of one of these great voids and somehow see the large-scale structure around us, we would find ourselves surrounded by faint, distant walls of galaxies on the horizon of the observable distance. The nearest substantial collection of matter would be hundreds of millions of light-years away in any direction. The immensity of such emptiness is difficult to fathom. It reminds us that while the universe has magnificent structures, those structures are stretched across a vast backdrop of almost total darkness. Paradoxically, these vast absences make the structure of the universe more evident. Like pauses in a symphony, they give shape to the cosmic melody of matter. By framing the luminous galaxies with expanses of darkness, the voids accentuate the patterns of the cosmic web. There is a stark beauty to this arrangement. Clusters and filaments stand out sharply against the silent voids that surround them. In their stillness, the voids impart a sense of cosmic tranquility. These are regions where, for eons, very little changes. The usual dramatic events of the universe, star formation, supernovae, galaxies colliding, happen rarely, or not at all, inside voids. Time flows quietly there, marked mainly by the subtle expansion of space and the gentle thinning of the already sparse gas. One can imagine the voids as the universe's great resting places, vast calm expanses where the fervent activity of creation takes a long hiatus. Drifting through a cosmic void in our minds, we might feel a profound solitude, but also a sense of peace. It is as if we have entered a grand, silent cathedral of space, where light and matter are scarce and silence is dominant. Yet, even in these enormous gulfs, we are reminded that we remain connected to the whole. The voids are threaded by the pull of gravity from distant masses, and ultimately, they too are part of the universe's fabric. And on the smallest scales, as we have learned, distance can be deceiving. Quantum entanglement can link particles across cosmic distances, hinting that separation is not absolute. In a way, the voids are as much a part of the cosmic tapestry as the galaxies are, defined by the very structures that surround them. To explore the idea of connection, even in separation, we now leave behind the vast scales of emptiness and journey into the subatomic realm. There, we encounter the phenomenon of quantum entanglement, which will challenge our notions of distance and individuality, and lead us toward the idea that our reality may be one of many threads in a much larger multiverse. On the tiniest scales of nature, a profound mystery unfolds, hinting that the universe is more interconnected than it seems. Imagine two particles born together in a fleeting moment, like twins separated at birth. Even if these particles fly light years apart, an uncanny bond can link them. Change one, and the other responds instantaneously, as if an invisible thread stretches between them across space. This phenomenon is known as quantum entanglement. Albert Einstein famously called it spooky action at a distance, because it defied the understanding of cause and effect of his time. How could something happening here affect something over there with no time delay? It seemed to violate the principle that nothing can influence anything else faster than light. Yet, over the past several decades, careful experiments have repeatedly confirmed that entanglement is a real feature of our universe. Particles separated by vast distances can indeed behave as one, their properties mysteriously intertwined in a way we are only beginning to comprehend. To grasp how strange this is, consider a simple analogy. Imagine you have two coins that are somehow linked, and you send one coin to the moon and keep the other on Earth. Whenever you flip the coin on Earth and get heads, the coin on the moon instantly shows tails, and if you flip and get tails, the distant coin shows heads. No one flipped the lunar coin. It just knows what happened on Earth and adjusts accordingly. And if someone on the moon tried the same, your coin on Earth would instantly respond. This analogy is crude, but it captures the flavor of entanglement. Two objects behaving like a coordinated pair, no matter the separation between them. Unlike the coins, quantum particles don't have a definite face until measured, but once one takes on a value, the other is instantly forced into the corresponding value. Importantly, there is no usable signal being sent between them in that moment. If there were, it would violate the laws of physics as we know them. Entanglement just is, built into the fabric of reality in a way that transcends classical concepts of space and time. Entanglement suggests that separation might be an illusion at the deepest level of existence. It's as if when the universe was born, it wove certain parts of itself together, so that even when those parts drift far apart, a hidden connection remains. When we observe one entangled particle and find, say, that it is spinning up, its distant partner is instantly found to be spinning down, no matter if they are a laboratory apart or on opposite sides of the galaxy. There is no discernible force that travelled between them in that instant. It simply happens, silently and inevitably. This phenomenon has been measured not just across rooms, but across cities, mountaintops, and even between Earth and satellites in space, always with the same result. Quantum entanglement holds. It's as if the two entangled particles are not truly two separate entities, but a single system sharing one existence. They only make sense when considered together, no matter how far apart they may be in space. This counterintuitive truth about nature invites us to rethink some fundamental assumptions. If two tiny bits of matter can be so deeply linked across cosmic distances, what does that say about the fabric of reality? It hints that on a fundamental level, the universe is a unified whole, with threads connecting distant parts in ways our classical ideas fail to capture. Some have poetically suggested that perhaps all things are connected, since everything emerged from the same primordial fireball of the Big Bang. Entanglement is like a ghostly echo of that initial unity, a reminder that the universe has an underlying coherence that we are only beginning to glimpse. It doesn't allow us to send messages faster than light or break the rules of causality, but it does show that the universe's rulebook is more nuanced and magical than we once thought. Such a strange discovery naturally expands our imagination about what is possible. If two particles can be linked across light years, some physicists asked, could it be that what we perceive as a single outcome is just one facet of a larger reality? This line of thought leads to one of the most astonishing ideas in quantum theory, the many worlds interpretation. According to this interpretation, whenever a quantum event has multiple possible outcomes, all outcomes actually occur, but each in its own separate branch of reality. In this view, Measuring one entangled particle doesn't mysteriously send a message to its partner. Instead, the act of measurement causes the world to split into branches. In one branch, we happen to see the first particle in state A, and the second particle immediately adopts state B. In another branch, the first particle is in state B, and the second in state A. Both outcomes happen, each in a different universe, and within each universe the laws of physics, including the consistency of entangled pairs, hold without any violation. The notion of parallel worlds has been a staple of imaginative fiction and philosophy for ages, but here it arises as a natural implication of quantum physics. It's a mind-bending concept, a constantly branching multiverse where countless versions of reality exist in parallel, every quantum possibility realized in some world or another. Beyond the quantum realm, the idea of a multiverse also emerges from cosmology and other theoretical considerations. Our universe, vast as it is, might be just one bubble in an infinity of bubbles, frothing up from a larger cosmic expanse. The theory of cosmic inflation, a brief era of exponential expansion that many scientists believe occurred instants after the Big Bang, suggests that different regions of space could have ballooned into separate domains, essentially becoming separate universes with their own laws and properties. Each such bubble universe would be disconnected from ours, forever out of reach, with perhaps different fundamental constants or forms of matter. In some universes, stars and galaxies might not form at all. In others, they might, but with different elemental mixes or physics shaping them. There are also ideas from advanced physics, such as string theory, that predict a vast landscape of possible universes, each corresponding to different ways to set the basic parameters of physics. The number of potential universes in these models is almost incomprehensibly large, perhaps effectively infinite. If a multiverse of some kind exists, it fundamentally changes how we see our place in the grand scheme. Our observable universe, with its hundreds of billions of galaxies, could be a mere drop in an endless ocean of universes. Some scientists have even suggested that the existence of a multiverse might explain why our universe has the life-friendly properties that it does. We often marvel at how well-suited the physical constants and laws are for the development of galaxies, stars, planets, and ultimately life. It could be that in a multiverse containing every possible variation of cosmic conditions, we naturally find ourselves in one of the rare universes that happen to have the right conditions for our existence, because only those universes get observers. In that sense, our universe may feel tailor-made for life, not by necessity or design, but by a kind of cosmic selection bias within the multiverse. Out of a vast ensemble of universes, life arises only in the Goldilocks ones that have just the right conditions. The multiverse idea, admittedly, is highly speculative and difficult to test. By its very nature, if other universes are completely separate, we might never get direct evidence of them. Some critics note that a concept untestable even in principle is more philosophy than science. But others point out that the multiverse could leave indirect clues, or that it might become testable in ways we haven't yet imagined. Regardless, contemplating the multiverse stretches our perspective and invites a profound humility. It means accepting that what we can see and measure might not be the whole story of existence. It might not even be a large fraction of it. We, with all our telescopes and theories, could be gazing at just a tiny sliver of a far greater reality. And just as entanglement hints at hidden connections within our universe, the multiverse hints at hidden realms beyond it. Entanglement and the multiverse both encourage us to expand our sense of what is possible. They show that the cosmos, whether on the microscale of quantum links or the macroscale of multiple universes, is richer and stranger than the world we perceive with our limited senses. These concepts also remind us of our limitations. There is so much we still don't know, and perhaps we'll never know, and yet there is great beauty in that unknowing. It means there will always be something to explore, some wonder to uncover. As we ponder these deep mysteries, we feel a mix of awe and humility. Our universe has allowed us, beings of stardust and curiosity, to reach out with our minds and uncover some of its secrets. But it also continually shows us that there is more, always more, beyond the horizon of our understanding. After journeying through these extraordinary ideas of particles that defy distance and of possible worlds beyond our own, we return our focus to the universe we directly inhabit. It is only natural to wonder what destiny awaits this cosmos of ours. All things in nature have a life cycle. Stars are born and eventually die. Galaxies evolve and interact. What then is the fate of the universe itself? In the next and final leg of our exploration, we peer ahead into the far future, toward the edge of forever, to glimpse how the cosmic story might unfold and perhaps conclude. At this ultimate horizon of time, we seek to understand the ending chapters of the grand cosmic narrative, the fate that awaits the expanding universe we call home. Time carries all things forward, and even the universe itself is not eternal in the form we know. As we peer into the distant future, we see the continuation and culmination of the trends we have observed. Galaxies will keep drifting farther apart under dark energy's relentless push. Star by star, the cosmos will slowly grow darker and colder. This journey into the future spans an almost inconceivable expanse of time, far beyond the lifespan of any star or planet we know today. In roughly 100 trillion years, 10 or 14 years, the era of starlight will draw toward its end. By then, the raw material for new stars will be mostly exhausted. The galaxies, now far separated from one another, will no longer have the cool gas needed to forge bright young stars. The great stellar factories will shut down. The remaining stars, born in earlier epochs, will age and die one by one. Mighty blue giants and yellow suns will have long since perished. Even the most stubborn red dwarfs, which burn their fuel so slowly they can shine for trillions of years, will finally begin to wink out. As the last generation of stars fades, the universe enters its retirement phase, often called the degenerate era. This is a time when the primary sources of light are no longer living stars, but the dim leftovers they leave behind. The night skies, in those far times, would be lit mainly by the faint glow of white dwarf embers and the occasional spark of energy from exotic events like neutron stars merging or evaporating black holes. As eons pass, even those faint lights will dwindle. White dwarfs, the hot cores of dead sun-like stars, will cool over quadrillions of years into black dwarfs, frozen spheres of carbon and oxygen emitting virtually no light. Neutron stars, which are the collapsed remnants of more massive stars, will also cool and fade, though they may remain as ever-present, invisible masses. Planets, if any still circle these remnants, will find their suns gone dark and their surfaces frozen solid. Some planets will have been ejected into interstellar space by gravitational tugs long before, wandering eternally in darkness. Galaxies themselves will change. Without new stars, they will be composed of old, dim stars and stellar corpses. Over extremely long spans, even these remnants will start to disperse. Close passes between stellar remnants can fling them out of galaxies, and those that remain may spiral slowly into the supermassive black holes at the galactic centers. Eventually, what once was a galaxy could be reduced to a diffuse cloud of dead worlds and black dwarfs, barely held together by gravity, and a central black hole quietly consuming stragglers. Trillions upon trillions of years hence, black holes will dominate the landscape of what's left. They will be the last substantial reservoirs of mass in the universe. Yet even black holes do not last forever. Stephen Hawking theorized that black holes slowly evaporate by emitting a trickle of Hawking radiation, a quantum process where particle-antiparticle pairs steal away a tiny bit of the black hole's energy. For massive black holes, this process is incredibly slow. A black hole with the mass of our Sun would take about 1067 years to evaporate. More massive ones, like those in galactic centers, would take on the order of 100 years, a number with 1 followed by 100 zeros. But given enough time, even the mightiest black holes will evaporate. They will shrink gradually, becoming hotter and radiating faster as they lose mass, until in their final moments, they release a last burst of energy and wink out of existence. In those final flashes, after an incomprehensible stretch of darkness, there will be brief flickers of light again as the last black holes die, but to no audience in the silent, empty cosmos. After the final black hole evaporates, the universe will have reached a state of profound simplicity and stillness. No stars shine, no concentrated mass remains that can collapse or ignite. The cosmos is effectively a thin haze of elementary particles and very long wavelength radiation, almost uniform, and at a temperature only fractions of a degree above absolute zero. This scenario is often termed the heat death of the universe, or the Big Freeze. It is a state of maximum entropy, where all energy is evenly spread and no useful work can be extracted from it. In this final era, sometimes called the Dark Era, the universe will be unrecognizable. All that remains are ghostly photons, neutrinos, electrons, and positrons, sparse and isolated, each chasing its own path through an ever-expanding void. If protons, the hearts of atoms, are unstable, they would have long decayed by now, dissolving any remaining matter into radiation and leaving not even cold rocks behind. If protons are stable, then perhaps black dwarf stars and other degenerate remnants might still drift, but they would be inert and effectively invisible. Loneliness embodied as matter. It is a melancholy picture, an end not with a bang, but with an eternal sigh. The cosmos that was once vibrant with galaxies, stars, and life will have become a quiet, endless night. A universe that was full of galaxies, stars, and planets will be a nearly featureless expanse. Yet it's important to remember how vastly far in the future this demise lies. We are talking about timescales that dwarf the current age of the universe, roughly 13.8 billion years, by factors of trillions upon trillions. The universe still has a long and eventful life ahead by human standards. Stars will continue to shine for many trillions of years, and even after starlight ceases, black holes and exotic processes will carry the story on. Any beings pondering the fate of the cosmos today, like us, live in what might be considered the springtime of the universe, a time rich in light, diversity, and possibility. The deep winter of the cosmos won't set in until far, far beyond any time we can truly grasp. It's also worth noting that our projections of the future assume the laws of physics, as we know them, remain constant. There is always the possibility of surprises. Dark energy, for instance, seems constant now, but we cannot be absolutely sure it won't change. If it were to increase in strength, an idea known as phantom energy, the expansion could accelerate to the point of tearing apart galaxies, stars, and eventually atoms in a catastrophic Big Rip. Current data suggests this extreme scenario is unlikely, but it remains a theoretical possibility. Conversely, if dark energy were to fade or reverse sign, something we have no evidence for but cannot rule out entirely, the universe's expansion might slow and perhaps eventually stop, leading to a scenario where gravity causes a big crunch, a sort of reverse Big Bang. That possibility appears remote given what we observe. All signs indicate an ever-expanding, cooling universe. In contemplating these ultimate fates, we find a mixture of awe and poignancy. The sheer scale of time and change we are imagining dwarfs all human experience. It humbles us, but it also illuminates our moment. Here and now, under the warmth of a star, and in the glow of countless galaxies, life has the chance to flourish and understand. Our epoch, with galaxies bright and the sky full of stars, is special and finite. Knowing that the cosmos will not always be so vibrant gives an extra preciousness to the present. It encourages us to treasure the beauty of a starry night, the burst of a sunrise, the delicate glow of a distant galaxy in our telescopes. These are the cosmos in its lively youth and middle age. There is also a kind of peaceful acceptance that comes with this grand perspective. The universe's story, like every story, has chapters, a beginning, many middles, and an end, or at least a profoundly quiet asymptote. We happen to find ourselves in one bright chapter, and we can imagine the outline of the final chapters, even if none of us will be there to witness them. In a way, the cosmos is like a brilliant flame that will eventually cool. But that knowledge does not diminish the flame while it burns. In fact, it makes it all the more beautiful and meaningful. It reminds us that all things, even universes, evolve and change. Standing at this imagined precipice of forever, gazing toward an almost infinite future, we feel the weight of deep time. It reminds us of our smallness and also of our connectedness to the cosmic story. We came from the universe's past, from the explosive birth of stars and the fusion of elements, and we are part of its present. In some sense, through our understanding and curiosity, we also become witnesses to its far future in our minds. The end of the universe, as remote as it is, teaches us to value the here and now. It urges us to seek meaning, not in the everlasting, but in the transient and the precious. And so, as we conclude this exploration of cosmic destinies, our thoughts turn back to ourselves, to the beings made of stardust who have contemplated all this. What does it mean for us, small as we are, to be part of such a grand and fleeting cosmos? In our final reflections, we will search for the emotional and philosophical meaning of everything we have seen, the perspective gained from confronting darkness and wonder on the largest scales, and how it shapes our understanding of our own lives and our place in the universe. For as long as humans have existed, we have looked up at the stars with wonder. Our distant ancestors saw figures in the constellations and felt the sky's majesty without understanding its true nature. Today, our knowledge has grown by leaps and bounds, yet that wonder remains and is only amplified. We end our journey not in darkness, but in reflection on ourselves and our place in this vast cosmos. We journeyed from the strange gravity wells of black holes to the invisible scaffolding of dark matter, from the expansive force of dark energy to the silent expanses of cosmic voids, and even pondered the quantum threads of entanglement and the possibility of other universes. Now, having roamed through these cosmic wonders, we find ourselves once more on the small world where our experience resides. After exploring black holes and invisible matter, cosmic voids, and quantum mysteries, we return to the simple fact that we are here, tiny, thinking creatures on a small planet, contemplating the universe. It is a profound truth that the iron in our blood, the calcium in our bones, the oxygen we breathe, were all forged in the hearts of stars. We are literally made of stardust, built from the elements created in stellar furnaces and supernovae long before the Earth existed. The universe is not just around us, it is within us. Each of us is a miniature cosmos, a collection of ancient atoms that have seen the inside of stars and drifted across interstellar space before coming together to become us. And within this living collection of stardust arises something equally remarkable: consciousness, the human mind, the capacity to wonder and to create meaning. This is what we might poetically call the soul or spirit, not as something supernatural, but as the emergent spark of awareness that lets us reflect on ourselves and the cosmos. Through our eyes, the universe can gaze upon itself. Through our minds, the cosmos can ponder its own nature. As the astronomer Carl Sagan said so eloquently, we are a way for the cosmos to know itself. In us, the ancient atoms and energy of the universe have coalesced into a form that can appreciate beauty, experience curiosity and love, and seek meaning. The cold expanse of space has, in at least one corner, blossomed into thought and feeling. The realization of our cosmic origins and our tiny place in the whole can be both humbling and elevating. On one hand, we see how small we are, just one species among countless others on a fragile world, orbiting one star out of billions, in one galaxy out of trillions. From a cosmic perspective, the divisions and conflicts that often consume us truly fade into insignificance. Seen from afar, say, from the vantage point of a spacecraft at the edge of our solar system, Earth is a pale blue dot, a single pixel of light in a vast darkness. Astronauts have described a profound overview effect upon seeing Earth from space, a sudden realization of our shared home and fragility. The cosmic perspective extends that feeling to encompass the entire universe. In that tiny pixel lies everything we hold dear, every story ever told, every city ever built, every drop of ocean, every leaf, every loved one. Recognizing this unity and fragility can fill us with compassion and a sense of shared fate. We are all passengers on the same small planet, a solitary raft in a great cosmic ocean. The cosmic perspective makes it clear that the only home we have is this one, and it is precious. It inspires us to cherish our planet and to see all people as fellow voyagers, fundamentally more alike than different. On the other hand, understanding our connection to the cosmos can be deeply inspiring and empowering. If the universe seems overwhelmingly large and ancient, we can also marvel that we have the privilege to witness it. For however briefly, we get to partake in the grand play of existence. We have the ability to uncover the universe's secrets, to send spacecraft to other planets, to look back in time with powerful telescopes, and to unravel the mysteries of matter and energy. We have cracked open atoms, listened to the echo of the Big Bang, and peered at galaxies billions of light years away. These achievements are the collective spirit of humanity at work, our drive to know, to explore, to find meaning beyond our immediate needs. In a way, It is an expression of the universe's own curiosity, manifested through us. Far from making us feel insignificant, this knowledge can make us feel profoundly fortunate to be alive at a time when we can understand these truths. There is also comfort to be found in the cosmic perspective. When confronted with the immense scale of space and time, our daily worries, and even many of our differences, can be put into a gentler context. This is not to say our lives are unimportant. Rather, it highlights how precious our lives are in the face of cosmic vastness. Some even sense a spiritual awe in this perspective, a reverence for the cosmos that transcends traditional religion, rooted in the profound beauty of knowing we are part of a vast, interconnected whole. The universe may not have an inherent sentiment or purpose that we know of. It may be indifferent to human joys and sorrows. But that does not render our joys and sorrows meaningless. In fact, it is we who imbue the universe with meaning by experiencing it. The rarity and brevity of life make it all the more sacred. Knowing that our atoms will return to the cosmos one day, perhaps to become parts of new stars or planets or life forms, can be a comforting thought. A part of us is immortal, woven into the fabric of the universe itself. And our actions, our love, our knowledge can ripple outward, affecting the future far beyond our brief lifetimes. We are transient, but we are also part of eternity. As we conclude this journey, we carry with us a sense of both awe and peace. The darkness we explored was not something to fear, but something that holds endless wonder. Each mystery of the cosmos, the black holes, the shadowy matter, the silent voids, the entangled particles, has deepened our appreciation for how marvelous existence is. The more we learned, the more we realized that there is a profound beauty in not knowing everything, in the endless pursuit of understanding. There will always be new mysteries to explore, new wonders to uncover. That is a comforting thought. The story of discovery is far from over, and perhaps it never will be as long as curiosity survives. Under the canopy of stars on a clear night, one might feel small, yet also profoundly connected to all that is. We feel the tug of gravity anchoring us to our world, the gentle light of distant suns touching our eyes, the echo of the Big Bang in the quiet between radio static, all reminders that we are part of the universe. In our minds and hearts, the universe has awakened to itself. In the face of cosmic darkness, we have found not despair, but a deep sense of wonder and belonging. And in that wonder lies a gentle hope. Hope that as long as there are beings who look up at the sky and ask, why, the cosmos will never be truly cold or empty. Because through our curiosity and our love, we give the universe meaning. Our voyage through darkness and wonder comes to an end, but the journey of the cosmos continues, and so does our own journey of understanding. We return now to the present moment, standing on our small planet, bathed in the light of a humble star. We carry with us the knowledge that even in darkness, there is beauty, that we are made of the very stuff of stars, and that our capacity for wonder is one of the greatest gifts the universe has given us. With hearts full of curiosity and humility, we look up at the stars, our celestial ancestors, and we feel at home. In the vast darkness, we have found light and meaning. In exploring the cosmos, we have discovered ourselves. And as we bid farewell to the cosmic night, we do so with gratitude, amazement, and a quiet sense of peace, ever mindful of the enduring bond between the stardust in our bones and the endless wonder of the universe.